Hello. So Kepler's laws were known as laws of planetary motion. There are three of them, and they are all based on the shape that he found when he plotted the data from Tycho Brahe and his own data. When he plotted that literally, he found that it wasn't a circle. It was actually just 1 to 3 degrees off of a circle, depending on the planet. And the orbits were still an ellipse, because an ellipse can be a circle, an ellipse can be an oval. But this was just off of a circle. So this concept of the shape of an ellipse is not new to him. It was actually devised 500, 600 years BC, known to the Greeks very well. And to go over it with you a bit, ellipse again is a plane that intersects a cone, like we described in the first lecture. And in doing that, the way you draw an ellipse, or the way you find it that shape, is by taking two thumbtacks, and those two thumbtacks become two focus points. It can be anywhere you want. Two thumbtacks. Then think of a string that you post between those two thumbtacks, and a pencil in the in this angle right here. And take the pencil all the way around, and you've drawn an ellipse. It is the shape that you will get when you use two thumbtacks, that string, and that pencil. Now, one of the hallmarks of this shape is that when you take the distance to the pencil and you take the distance back to the other thumbtack, that distance will be constant anywhere on the ellipse. So you could have a distance like this. It would be constant to the L1 plus L2. You could have a distance like this. It would be constant to the L1 and L2 that you see there, constant all the way around. That is the definition of the ellipse. As you can see, that could definitely happen in a circle, and it could definitely happen in an oval. In this case, when Kepler was looking at his data and finding the ellipse, he hypothesized that one of the focus points is the sun. And the sun would be at one focus point in the ellipse. The other focus point would be some point in space. It didn't matter where the point was. The point wasn't defined, because remember, he's plotting out data. So he doesn't really need to know the other focus point. He just needs to know that one of the focus points is the sun. We went over how to draw an ellipse. Sorry, not an eclipse, an ellipse. We went over how to draw them. And ellipses can be circles, especially when the focus points are identical. So when you have the focus points is identical, and you had two thumbtacks right on top of each other, and a string between the two thumbtacks, you'd go around in a circle. And if you had the two thumbtacks way out here, that string would go all the way around in a very broad oval. I think I say that right in the next slide here, okay? When the focus points are wide apart, you have an oval ellipse. When they're very close together, you have a circle. You'll be doing this as part of your homework. You can also note, and we'll bring this up in the assignment, eccentricity. They talk about eccentricity of an orbit. And when you have the focus points far apart, you will note an eccentricity that is close to 1. When you have the focus points very close, say the eccentricity is closer to 0. Eccentricity is actually a construct. It's actually a mathematical construct. It is the distance from the center to one of the focus points over the distance from the center to the farthest point from the center. Now, let's talk about this. If you're very, very close to a circle, remember the The farthest point from on a circle from the center is going to be the radius, right? From point to point on a circle is diameter. Half of diameter is a radius. So because these are very nearly circles, we're just going to say this is the distance from the center to one focus, this distance right here, over what's basically an average radius. That makes sense, right? Now, in astronomical terms, they're going to say that this is the distance from the center to one focus over the semi-major axis. So when you do this, you'll have that in your assignment, but it'll all be laid out for you. And you hear about the eccentricity as C over A. C is the distance from the center to one focus, and A is the axis, the semi-major axis, which is basically the average radius. All right. The eccentricity of the orbit, Mercury happens to have the most oval orbit. Mercury has the number that is closest to 1, and it's not that close to 1. The Earth has an orbit that is very close to 0 for eccentricity. Kepler's second law of planetary motion. He said that he noticed in putting the sun at one focus and the planet out in his ellipse, he noticed that the speed of the planet, because he knew all of this data, the speed of the planet seems to increase the closer it is to the sun. And the speed of the planet seems to decrease the farther away it is from the sun. And he noticed that, and all the calculations said that. His second law of planetary motion says that it acknowledges the speed difference, but in the ellipse, amazingly, beautifully, the area carved out by a line between the sun focus and the planet covers the same area in the same amount of time all the way around the ellipse. You say, wow. Okay, hold on a second. So if you had a string attached to the sun and attached to the planet, and this planet was racing past here, it would cover the same amount of area as a string attached to the sun and the planet all the way out here where the planet is going more slowly. All of these areas, A, B, and C, are identical. And it is very beautiful mathematically to think about that. The total area swept out across the entire ellipse for these planets is the same. Kepler did not know why this happened. He needed to wait for Newton to tell him all of this. Newton put it all together. But if you're thinking about the big three here, you're basically thinking about Kepler, Galileo, and Newton working together on this over about 100 years. And this second law was a puzzle that was solved a little bit later, but the mathematics was done by Kepler. We've talked about that. The third law that Kepler had related the orbital period, the amount of time it took for a planet to go around the sun once in a planetary year. It related that orbital period to the average radius of that planet from the sun, the basic average radius of that planet from the sun. We can talk about that specifically. The orbital period is the period that the time that a planet takes to travel around the sun once. That average radius that we were talking about, remember it has a name. The name is semi-major axis, so that there's a relationship between these 2 points. This is the orbital period. This is the semi-major axis, basically the radius. When you apply specific units to those proportional things, the radius and the orbital period, you get an equality that is really pretty outstanding. And the equality is this: if you square the orbital period in years, it will equal the astronomical unit, the distance between the sun and the earth, cubed. And this goes for any planet. This goes for Jupiter and Saturn and Neptune. If you square their orbital period around the sun, it will equal the number of astronomical units, meaning the distance between Earth and sun cubed. It's really quite beautiful, and mathematicians love this for the beauty of it. So I will give you one little proof of this. Now, we can do the really simple proof, and the really simple proof is the Earth, because the Earth is one astronomical unit between Earth and sun. So let's do, and the Earth has 1 year for an orbital period. So let's do this. Here's the astronomical unit. Here's Earth at 1. So if we cubed the astronomical unit, 1 times 1 times 1 equals 1. And if we squared the period of 1 year, we would get 1 times 1 is 1. So that doesn't really tell you very much, but it does work. And let's look at Jupiter, because that's a little bit better. If you looked at Jupiter and you said the astronomical unit, the distance of the sun to Jupiter is 5.2 times the distance between the sun and Earth. And let's say you rounded that down to 5. If you cubed 5, you would get 5 times 5 is 25. And 25 times 5 is 125. Okay? Keep that in mind, 125 for that cube on that AU. Now, if I did it on my calculator, I would get 5.2 times 5.2 equals 140.6. Okay, 140.6. And let's say you took that 11.86 for the orbital period in Earth years. Let's say you rounded it up to 12. 12 times 12 is 144. What is 11.86? 11.86 times 11.86 equals 140.6. Okay? So there's your proof. You can do it in your head, 5 times 5 times 5 and 12 times 12, and come pretty close to it. But this third law is a very beautiful law that mathematicians love, and I hope that you'll keep it in the back of your head. Let's go on to Galileo next, because he's part of the big three that just flipped the scientific world on its ear.